This is on page 96 when we're done. Okay? So recall means we already know this or we've already talked about it, right? It says we first introduced tangent in 3.2. We actually did it before that. But one of the things that was introduced to us in 3.2 was one of the ways we look at tangent, with tangent being the slope of the terminal ray. Okay, and that's something that got some of y'all stumped on the review yesterday. Or as the ratio of the angles sine to cosine. That's something we already knew. We talked about it sine over cosine, y over x. But then when we started unit 3, we also looked at it as the slope of the terminal ray. So here is the terminal ray, right? And it is part of a line that would look like that. And we know one way we can write an equation of a line is y equals mx plus b. Well, being a terminal ray, that line will always go through 0, 0, which means your y-intercept is 0. So we really just have y equals mx, which is what is written right there. And then if I divide both sides by x, I get y over x equals m, which is the slope. And we also know that y over x is tangent theta, and that is why the slope is the tangent value. Okay? Rise over run. And that's why if we have a terminal ray in the first or the third quadrant, like we have drawn right there, that has a positive slope. That's why tangent is positive in the first and the third quadrants. And then if it's going through the second and fourth, then that would be a negative slope, and that would be negative tangent values. Okay, make sense? Along those same lines, just as a little side note, if, and you don't necessarily have to draw this part, but I just want to kind of, I don't know that I've ever really said it this way. In the unit circle, is sine x or y? Y, okay? So that's in a y equals line is a horizontal line, right? So if I have a horizontal line going through my unit circle, and that's up on my positive y values, that's why sine is positive in the first and second quadrants. If the horizontal line was down here, it'd be in my negative y values, and that's why sine is negative in the third and fourth quadrants. Cosine is the x value. Vertical line going through my, maybe I should make it actually look like it's going through the circle. Going through my circle here, in the positive x values, cosine's positive in the first and fourth quadrants. If I drew my line over here on the negative x values, that's when cosine's negative in the second and third quadrant. So just another way to look at it, because there's different ways you can, keep all that straight in your mind, but just kind of want to connect all the lines and the slopes and stuff together. Okay? All right, so then let's look through these little circles here. So we're going to look at the slope of the terminal ray, and here, this terminal ray, that angle is just at 0. And what is the tangent of 0? What's the slope of this line? 0. Okay? And then this angle here, we're going to make that pi 6th, because I want to be able to label these. What is the tangent of pi 6th? Square root of 3 over 3. Okay? Square root of 3 over 3. Then this one is pi 4ths. What is the tangent of pi 4ths? 1. This one, we're going to label it as pi 3rds. It's not exactly pi 3rds, but once we label it, we can pretend, and it's fine. Pi 3rds, what's the tangent of pi 3rds? Square root of 3. Okay. So now look at the slopes of those terminal rays, okay, and the values. The slopes, it gets steeper and steeper, right, and the values increase. Now, this one, it's getting really close to pi halves, right? Don't know what the angle is, doesn't matter. But the closer and closer that this gets to pi halves, the bigger and bigger the tangent value gets, right? So that means the bigger and the bigger the slope gets until it gets infinite. And then when you actually make it to pi halves, what's the tangent of pi halves? Undefined, okay? So that's what this basically says right here. When theta is 0, the slope is 0. As theta increases, the slope also increases. As theta approaches pi halves, the slopes get steeper and steeper, or more and more positive. So when theta hits pi halves, the terminal array is now vertical. That is this right here. Okay, so this right here, this is pi halves. And the slope of a vertical line, we know is undefined. So when we say the slope is undefined, it is because it is infinite. The limit as theta approaches pi halves from the left is infinity. And that's because the tangent of pi halves is undefined. Okay? Now let's move into the second quadrant and look at that. We're going to start with this one. We'll say that this is our second quadrant pi thirds angle. What's our second quadrant pi thirds angle? 2 pi thirds. Good. 2 pi thirds. And then what is the tangent of 2 pi thirds? Negative square root of 3, right? It's square root of 3 because it's a pi thirds angle. It's in the second quadrant. And also, if you look at that terminal ray, that would have a negative slope. That's what makes it negative, okay? Then this angle right here, we will make this our second quadrant pi fourths angle. So what's that? 3 pi fourths, good. And what is the tangent of 3 pi fourths? Negative 1, very good. Then we'll make this our second quadrant pi sixths angle, even though it's a little off. What's your second quadrant pi sixths angle? 5 pi sixths, very good. And then the tangent of 5 pi sixths is? Negative square root of 3 over 3, good. All right, what's this angle? Pi, all right, once we get all the way around there. And what is the tangent of pi? 0, right? So if we're thinking on a number line, we got negative square root of 3, moving on to negative 1, negative square root of 3 over 3. As this goes around here, the tangent values are getting closer and closer to 0, so they're actually getting bigger, but they're getting closer and closer to 0. Slope is negative, right? So we can see from pi halves to pi, the slopes transition from negative infinity to 0. Okay? All right, flip it over. We're going to do the third quadrant. We're going to skip the fourth quadrant, but okay, so we'll start with, we're actually just going to do 2 of these. We'll do this one. We'll make this here our third quadrant pi sixth angle. What would that be? 7 pi 6, good. And what is the tangent of 7 pi 6? Square root of 3 over 3. So we know that tangent's positive in the third quadrant, but we can also see that this is a positive slope, and then that's why it is what it is. And then we will make this our third quadrant pi thirds angle. What would that be? 4 pi over 3. Good. 4 pi thirds. And then what is the tangent of 4 pi thirds? Square root of 3. Then, so these kind of, and then they just, you know, the angles are changing here, but we get all the way to here. What is this angle? 3 pi over 2. Good. And then what is the tangent of 3 pi over 2? Undefined. Right? Because it's a vertical line, slope of a vertical line is undefined. Okay? We okay with all that? So that's kind of attaching it, or, you know, making it make sense with the unit circle. What we're getting to here is that each time the terminal ray is vertical, the slopes are undefined. We know that. When we graph the tangent function, so when I graph, and when we get down here, we start plotting things. If something is undefined, there's a couple of ways you can show it on the graph. What's one way you can show it? Open circle. That's one way. What's another way? This always takes y'all forever. And then once somebody says it, you're like, oh. Okay. So if I have an open circle, that means that somewhere along the way, something's not defined and I just kind of took a point out, right? Okay. That's totally one way to do undefined. That's not what's happening here though. So we need the other way. When I'm approaching infinity or negative infinity, what do I have on my graph? Asymptotes. Very good. So, what we will see are vertical asymptotes. Okay. All right. So with all that knowledge there, we're going to create our tangent graph based on what we know about tangent. So let's just plot some points here. What is the tangent of 0? 0. So when I'm at 0, it's 0, 0. There's a point. What is the tangent of pi fourths? 1. Okay, so we'll put a point at pi fourths, 1. What is the tangent of pi halves? Undefined. So that's where my vertical asymptote goes. Okay. So now we've gotten through the first quadrant of the unit circle. Remember, we don't care about these quadrants. Don't look at these. We're picturing the unit circle in our head. So we've gotten to pi halves, which gets us to the first quadrant. Now we're in quadrant 2. What do you know about tangent in quadrant 2? It's negative. So 3 pi fourths, the tangent of 3 pi fourths is negative 1. And then pi, what's the tangent of pi? 0. So that got us through the second quadrant, right? Now if from pi, we're going into the third quadrant. So what's the tangent of 5 pi fourths? 1. Then what's the tangent of 3 pi halves? Undefined, because that's a vertical line again, right? Okay, so now we've gotten through the third quadrant. So now we're into the fourth quadrant. What's the tangent of 7 pi fourths? Negative 1. And the tangent of 2 pi? 0. Okay, everybody good with that? Now before we actually sketch anything in, we can make some observations here. First, clearly, this is not going to look anything like sine and cosine, right? Those two are very similar. This ain't going to look anything like that. The second thing, but one of the things that it does have in common with that is that it is periodic, it does repeat, and things are spaced out all evenly. So before I even sketch anything in, I can figure out where some other things go and get the left hand drawn on here. These zeros are happening every pi units, right? So that means I can back up to negative pi and then negative 2 pi. Then I can see that my asymptotes are halfway in between two of the zeros each time. So halfway between these two zeros, I can, oops, cannot, never not to do that. Okay, there's one asymptote, and then halfway between these two, you get another asymptote. Right? Half, half, half. Everything's spaced evenly. Then I have these points up here, right? So halfway between a 0 and the asymptote on the right, I go up 1 each time. So halfway between my 0 and the asymptote to the right, I'm going to go up 1. Halfway between the 0 and the asymptote to the right, I'm going to go up 1. This, halfway between the 0 and the asymptote on the left, I go down 1. So then I can get those points in there. That looks really pretty. Okay, so now I've got to come up with a graph for this. Now, these 3 diagonal points that work right here, these are all linear, but I can't draw a line through it, because if I just draw a line through these points, it's going to poke through my asymptotes, and that's a big no-no. We can cross horizontal asymptotes. We absolutely cannot cross vertical asymptotes. So I can't do that. And the whole purpose of having an asymptote is that we are approaching it, right? So right here, I should be approaching it right here and approaching it right here. So it's actually going to look something like this. That 0 is a point of inflection. Okay? And you don't have to really overemphasize the point of inflection. Sometimes when we sketch these, people go crazy trying to make it, look really inflection-y. But think about a cubic. It's just not quite as curvy as a cubic on this particular graph. On some of them, they will. It just depends on how stretched out it is. But we can get all of this drawn in here. And then as you can see, definitely looks way different than sine and cosine. Do I have maximums and minimums here? No. Okay? You can't have a maximum and a minimum at infinity because that's not a number. So if I don't have a maximum or a minimum, I don't have a midline because the midline is halfway between the two, right? And then if I don't have a midline, I can't have an amplitude because the amplitude is the distance from the maximum to the midline and from the midline to the minimum. But that doesn't mean that A doesn't exist. It's just that A doesn't have a fancy name anymore. We only get the fancy name for sine and cosine, okay? And midline, we're going to pretend like we have a midline when we do these and draw in what I call the fake midline because it still helps us just like it did on the other ones, okay? Now, another difference here is what is the period? If I start here, how far do I go until I repeat? Pi, right? And this is the parent function. So the period for the parent function is pi, not 2 pi. And that's one of the things that you have to remind yourself on tangent because that's one of the most common mistakes. You just try and continue to use 2 pi because we've used it for sine and cosine. Okay? All right. So then the other thing is the parent function, what I want you to have in your head for the parent function. And I want to be this, I know this one's going to look weird, but I think it's good that we're consistent that we start at 0. We started at 0 with the sine, we started at 0 with the cosine. We're going to do the same thing for this and for the reciprocals when we get there. So I start here, right? Start at 0, and then this is the beginning of the period, this is the end of the period. So I have a point, this board doesn't like me to make points here and a point here, beginning and the end. Halfway between the two, I have a vertical asymptote. And then this goes up, this goes down, and the A for the parent function is 1. Halfway between the 0 and the asymptote, we go up 1 or we go down 1, right? And so I have a point here, and that's going to help me with, and you don't have to like plot all the points every time you draw the parent function. I just want you to see that here, that's how we're going to get all the pieces in the graph together. Okay? What questions you got at this point? All right. So then here we have this same thing. It just says tangent instead of sine or cosine. All of that is literally exactly the same. Here's what the differences are. The vertical dilation, still A, like it has been on every transformation. It's just not called the amplitude. Okay, because it doesn't fit the definition of an amplitude, but it still does the same thing, just like the amplitude does. Here's where the big change is, because this is pi and not 2 pi, and we got to make sure we don't mess that up. Okay, it works the same way. You do everything the same way if you want the period or if you want B, but you just got to make sure you use pi because of the parent function. And then these two, this is still called a phase shift. This is still a vertical translation. It just isn't called the midline. Okay, everybody good on all that? All right, so I'm going to give you the second page. I didn't have you pick up the second page because I didn't want you to see the tangent graphs. I know some of you have seen them before, but I know not everybody has, so I wanted to kind of discover that without you seeing this. Just trying to keep it secret. Let's do some examples. And you'll see that we're going to work these much the same way we do sine and cosine. There's just some obvious differences here. Okay, this is also going on page 96 when we are done. Okay, so we have this function. Before I even look at the question, let's just take care of some stuff here. I'm going to draw in the fake midline. Because remember, it's not really a midline, but we can still use it to help us. And we're going to figure out A and D pretty easily here. First of all, did this shift up or down any? No. So D is 0. A, here's how you figure out A. From the 0 that's on the midline, Here's the asymptote. Halfway between the two, you go up. And so halfway, I only went up 1, which means A is 1. Okay? That's how easy that is. I didn't even read the question yet. Okay? The question says, can be written as this, and this right here shows you that there is no translation left or right. And that makes sense because we know the parent function, right? The thing we want to draw looks like this. Okay? And this is here. Now, could I write an equation with a translation to the right pi halves? Yes. Or to the left pi halves? I mean, I don't need to make it complicated, but if I did, it would just be the exact same graph. Okay, so we already found A and D. D is 0. Now, let me say something about this. We did not shift and we did not stretch. By not shifting, D is 0. By not stretching, A is 1, not 0. This is an additive transformation. That's why 0 is okay. This is multiplicative, which means if I multiplied by 0, it goes away. Because I've seen some people want to put 0 for A because nothing changed. But you have to have that 1 there. Okay? Now, if I want to find B, excuse me, what do I have to know to find B? The period. So I start here, I end here, so what's the period? Pi halves, right? So what goes in the numerator when I divide? Pi, good. Pi over pi halves, and what does that give me? The pi's cancel out, so it's just 2. So you're right on the 2 part. Okay, we're good? What questions you got? Anything? All right, let's look at one without a graph. Even though it only asks us for the period, let's go ahead and just write some stuff out. What is A? 4. What is B? 2. What is D? 5. Okay? But I want the period. So period, which one of these 3 do I use for the period? B. Very good. And so in the numerator of the fraction goes what? Pi. I divide by B, which is 2, and then I'm done because there's nothing to reduce. That's your period. Okay? Everybody okay with that? Questions? Ask me a question. Ask me a question. Yes. Are you sure? Okay. All right. So now on this one, we have, let's just do the same thing here real quick. What is A? 2. What is B? 1/3. And what is D? -1. Okay. So then what is it asking me for? It is asking me for, it's asking me for the vertical asymptote, right? Now, there's a little formula I can give you for this and for a lot of things that we do. Let me tell you, you're not getting a formula chart and you will never remember them all and keep them straight. Maybe 1 or 2 of you, but most of us don't just have that little mind where it just prints stuff off for us. So instead, understanding the graph and what is happening is going to be way more beneficial for you because that is what kind of sticks with you anyway. Even if you do remember them for a while, they're so easy to get all mixed up. So let's just look at what's happening here. This is my parent function, right? This is one cycle of tangent with my parent function. I know that the asymptote is halfway between the beginning and the ending of the period. So knowing what the period is would be very, very helpful, right? This is here at 0. I want to know where this is for this particular graph. So I want the period. What goes in the numerator? Pi. What will go in the denominator? 1/3. Okay. And then in the end, that gives me what? 3 pi, right? Keep, change, flip. All right, so that means that it's going to take 3 pi units for one cycle to happen. Right? Then I've got halfway between the two is where this first asymptote is. So that's just going to be 3 pi halves. That's why it's easiest to start at 0. 3 pi halves. Then, because this is periodic, this is going to repeat every 3 pi units because that's my period and that's when it repeats. You with me on that? Now, if I look up here at my answer choices, because I figured this much out, I already know what my answer is, because this is the only one with 3 pi halves. But I want to talk about this piece here, because I could have 3 pi halves be at the beginning of every single one of these. Then we got to figure out what's going on with the second part, right? When we started Unit 3 and we talked about periodic functions, we hadn't even looked at trig equations yet, or trig graphs. And so we had these weird ones with line segments. And we were finding like f of 12. And remember, and we split it up. Let's say the period was 5. So we had f of 2 plus 2 times 5, right? Remember how we split that up because 5 was the period? That's what's happening here. We're saying this is my asymptote plus this is the period, and then it's going to repeat. So it'll be 3 pi away, and then 6 pi away, and then 9 pi, or negative 3 pi and go that way. So this will always be the period right there. That's why I kept pointing an arrow and I wrote period every single time. Remember that? So we're finding the period, we're using it to help us here, and then it also has to be in here. Okay? What questions you got? Worst case scenario, you could draw another cycle of it if you needed to, but I think you'll be able to figure them out. Okay. Let's look at this one. So we're going to start by drawing in our fake midline. That's not really a midline. We don't really have a name for it. So let's go ahead and find some things, just like we did on the rest. Let's find A. Okay, halfway between here and the asymptote, halfway I go up, and I only go up 1, so A is 1. Then we'll come back to B. What is D? Negative 2. Because that's where the midline is. That's not really a midline, right? Because the whole thing shifted down. So just by these two, and I usually skip B to start with because these are the easiest ones just to pull off. Can I eliminate anything based on this? Yes. B and D, right? And then if time's about to run out, I got a 50-50 shot now. But let's hope that we're not actually guessing. The only difference between these two are the B value, and that means I need to know the period. What is the period here? 2 pi. Let's start here and go to there. So period is 2 pi. When I go to find B, what goes in the numerator? Pi. So pi divided by 2 pi gives me what? 1/2. That looks like a plus. 1/2. Don't do something weird because look, one of the most common wrong answers I get in situations like this is 2 because it somehow magically comes out of the denominator. I know you know better than that. Don't make those mistakes. So that makes my answer A. Everybody okay with that? Yes? Good. All right, so I'm going to give you a minute or two, and I want you to fill in these values from your brain. You got this. I know you do. Am I hearing things? I swear I thought I heard somebody knock on the table. I hear people knock when there's nobody there. When they knock, I can't hear them. Don't look at the board. Use your brain. Okay, do you agree with my first row? Yes, we all agree with my first row. Do you agree with my second row? No. If we ignored the signs, would you agree with my second row? Yes, because that's all I did, was say, okay, this is the pi sixth angle, so this is a square root 3/3. This is a pi third. That's all I wrote up there. I'm not finished. Okay, because that's one part of the process, right? The other part is 5 pi sixths. Which quadrant is that in? Second. So in the second quadrant, that's what my terminal ray looks like. That's a negative slope. This is negative. 4 pi thirds, what quadrant is that in? It's in the third. That's what the terminal array looks like. That's a positive slope, so this one's good, right? 7 pi fourths, that is in which quadrant? Fourth. That's what the terminal array would look like. That's a negative slope. That's a negative 1, okay? Or you just know where it's positive and negative, which is totally fine too. Just another way to look at it, okay? Tell me what the angles in the bottom row, what do those 3 angles have in common? What kind are they? You know the fancy word? Starts with a Q. Quadrantal, yes. It's okay if you don't know the word as long as you know what to do with it. As long as you know that that's what they are. So 3 pi halves, that's down, that looks like that. That's a vertical line, so this is what? Undefined. Pi is over there, so this is 0. Pi halves looks like this, so this is undefined. Okay. All right, everybody good with that? Any questions at all? Awesome.